Hi, everyone. I'm Ignacio Arnaldo, and I'm happy to be presenting here today. I'm going to be sharing some of the challenges we're facing at Corelight to monitor our machine learning pipelines and some of the best practices that we have implemented. So first of all, about Corelight. Corelight is a company in the NDR space, so that's network detection and response. And the mission of the company is to help defenders by providing evidence and threat detections. The company has open source root with some of the co-founders actually building the Zeek open source project, which is a tool for network monitoring that is widely adopted. And please, I invite you to know more about what the company is doing in the company's website. When it comes to machine learning at Corelight, the machine learning models we develop are mostly part of a SaaS application. And the team that is building those models has a mix of experiences. So to create those models in our domain, in the network security domain, we need to have the security experts that are well aware of the domain. We need to have the data scientists that know how to model the data and how to create accurate models. And we need software experience to be able to put those models and take those from prototypes into production. So we do have that mix of experience that allow us to take things from those prototypes to production, as we have a very active role in that space, as well as the monitoring and maintenance, as we would see in this presentation. About myself, I have a background in academia with a PhD in computer science and experience as a postdoc. And back then I was mostly focusing at the intersection of machine learning and systems. And for the past 7 years, I added a third variable to that equation, which is cybersecurity. So I work at the intersection of machine learning, building systems to deploy machine learning, and focusing on cybersecurity use cases. So as we went more into the cybersecurity domain, one of the key questions was, okay, what is the role of machine learning here, right? And we soon identified that there were mostly two. One was to complement existing detections of, needless to say that cybersecurity is a complex space with very well-established solutions and processes. Solutions like IDS, intrusion detection systems, or SIEMs, in which, that have a very important role to play still today, right? And that already have some detections built in them. It's also important to think of SOC efficiency. So those are security operation centers where analysts actually go through the alerts, triage those, and respond to those. So anything we can do to help defenders do more in less time is going to be a big win. That said, there are many challenges for machine learning in this space, unfortunately. I broke those down into two big categories, modeling and deployment. For the modeling, I would say that obviously the biggest problem is that cybersecurity attacks are rare, right? So it's like looking for needles in haystacks, yet we are required to have models with very low false positive rates, because otherwise we would just like overwhelm analysts and they would not be able to act on the findings. Second piece is that there's many different types of attacks out there. If you're curious about it, I invite you to check the attack project that is run by MITRE, where they have descriptions of known attacks, and you'll see hundreds of them in there. To add to it, there's not a lot of label data, which means that we oftentimes have to craft our own data sets and do simulations and some magic so that we can actually create these models. Then when we go and actually deploy these models, we realize that no two networks are really equal, because networks might be set up differently, or because we might actually have different visibility. Models that work very well in one environment might not necessarily work in another. And the last piece is explainability. We do need to provide explanations and some background as to why the models think something is malicious, because those alerts are going to be reviewed by analysts, right? And we need to allow them to understand why the model is triggering that so that they can take next steps. And from a deployment perspective, as you can imagine, there's a lot of traffic going through the networks of large organizations. So we have the volume piece, and we have the requirement to identify threats in close to real time. Now, this is true about cybersecurity, that data is scattered across many different data sources and logs. And it's also true in the specific case of network security. Like if you think about it, there's a lot of protocols and applications that are stacked on top of each other, each of them containing different information. So it's important to understand those logs and to monitor all of those in simultaneously. And there are multiple entities that we need to model. So we have IP addresses. Anything on the network is going to have an IP address. But in some of those protocols and applications, we might also see users, domains, and other entities that are important to monitor. So as a result, we have these combinations of data sources, volume, and entities to track that lead us to have like very complex pipelines with many different paths. And that complexity, because of that complexity, is very important to have very good visibility into what's going on. To break it down, we have identified 3 different layers of observability. The first one would be infrastructure and performance, like is the system up and running? Are the components working? And are we generating results on a timely basis? The second one is perhaps the most complex because it has to do with data quality and correctness. And here is where we want to identify subtle issues like whether we're missing some data but not all, whether some data is not being parsed and processed correctly. And the third layer, this perhaps is the most expected one, is whether the models are generating value, whether the models are accurate and we're presenting value to the analysts that are receiving those alerts. So to deal with those, at Corelight, we have implemented some practices to instrument all of our machine learning pipelines that go into the product so that they can generate metrics. And then we use application performance management tools to create dashboards and alerts based on those metrics. And we have a continuous improvement workflow to, upon alerts of any issues or any of these levels, be able to respond to that and then improve the system to make it more robust as time goes by. In the next slides, I'm going to just provide quick examples of each of these layers and some of the metrics that we're using to monitor them. So for example, for the infrastructure in job, one good practice is to just measure input versus output rows at each of the stages of the pipeline. In this case, what I'm showing is the stage that is applying the machine learning models, that is taking feature vectors in and returning scores. And we see that there are 5 lines because there are 5 different entities that we're modeling. And it's a good practice to understand that each of those 5 pipelines is receiving some data, and it's also generating data out, right? And that there's a relation between the data that is coming in and the data that is coming out. The second layer, which is data correctness, as I said, is a little bit trickier. One of the things that we do is to monitor the number of entities that we're observing in the different log sources over time. So for example, if we're in a network where we know there should be like some 10,000 IPs, we can just track how many different IPs we see over time. And if that number falls below those 10,000, we know that we're probably missing data. So it's a good clue that we can follow up on. Another thing, perhaps more specific to our domain, is that the data might change, and that could make some of our parsing incorrect, right? And as a result of that, we might actually be missing important information in those logs, right? And a telltale of that could be that some of the features or some of the fields that we expect in there could have null values or 0 values. So one of the things we do is we actually count the proportion of nulls and zeros in our feature vectors and monitor that over time so that we can see anomalies in there. And finally, perhaps the most intuitive one is whether the models are generating accurate results. And while we cannot fully or get like feedback on every single alert that we generate, it is still possible to model things like the score distribution, right? Like if these models are supposed to find needles in haystacks, we could easily identify whether a model is finding way too many things. On the other hand, we also need to identify cases where models are not generating any alerts, because that could be that either the model is obsolete and not valid anymore, or that there is an issue in the preceding pipeline that is such that the model cannot see those attacks. And in those cases, we basically track those scores of the models over time to identify those situations. One other thing that we implement, or one other process that we implement at Corelight, is root cause analysis and remediation processes, right? So first, I think we need to take a step back and think of these complex systems as independent components. And for us, at least, it helps to think of it as an ML system has three big components, right? Or three main blocks. One is the models. The other is the data sets that are used to train the models. And the third piece would be the software or the systems that are put in place to deploy those models. And there are these complex dependencies between these three entities or components. And it's important to identify those very well. Now, in this case, I'm showing a dependency matrix that is true for one of our use cases, but it's not necessarily the one that applies to your own use case. So I would recommend you to do this exercise and try to identify these dependencies. The idea is that if, as we are monitoring the system, right, we identify that perhaps a model is not behaving correctly, right? We need to understand, okay, the model is not behaving correctly. Why is that, right? Is this the model itself that was not trained correctly? Is this because the data set that was used to train it was was not comprehensive enough, or was not properly labeled, for example? Or is it because the system that is deploying the model is faulty? Depending on each of those, we might have to take different actions. Now, we don't want those actions to delay us or set us back by weeks or months, right? So we need to have mature MLOps processes so that when we identify the root cause, we can actually regenerate those models and re-put those in production fairly quickly. So the first step of that, as I said, is to identify these dependencies and understand, okay, if a data set is wrong, what is going to have to happen for me to be back online as quickly as possible, right? These kind of dependency metrics helps with that. And then it's important to have those processes with as much automation as possible, of course, to be able to regenerate these models, data sets, and software, these artifacts, and put those back in production. So finally, key takeaways. This is something that I have, I think, said in other presentations, but it's true. I think it remains true. ML modeling work is just the tip of the iceberg. To put these models into production, there's a lot of work that needs to happen behind the scenes. As we said today, visibility into ML pipelines it's complex, right? There aren't that many out-of-the-box tools that you can use that would allow you to do that, as there are for other pieces of big data stacks. Infrastructure, we can get some of that help, but data correctness and quality of the results ends up being very application specific. So we need to instrument the pipelines to get that visibility and then build those monitoring and remediation workflows. And then last piece is to be able to be agile and react quickly to issues, we need to understand the dependencies between models, data sets that are used to train the models, and the software that is deploying those. So my recommendation would be to take that step back and do that analysis of those dependencies and establish those machine learning operation processes that would be able to handle those updates efficiently. So that's all from me. Thank you very much for listening. I'm very interested in knowing if you have experienced similar challenges and the solutions that you have implemented. So please reach out on LinkedIn. Looking forward to it. Thank you very much.